Hey, good evening, ladies and gentlemen. How's everyone tonight? Good. Well, as always, thank you very, very much for coming out to join us. Juno, the solar-powered spacecraft that has been orbiting Jupiter since July 4th, 2016, flies by the giant planet every 53 days, collecting a wealth of new information with each pass. The data collected so far have revolutionized our understanding of Jupiter and of giant planets in general. This talk will present some of Juno's current science results and discuss what we might expect in the coming years. Tonight's guest is the Juno Project Scientist and the lead co-investigator for Juno's microwave radiometer instrument. He has worked at the Jet Propulsion Laboratory since 1990, during which time his research interests have included the light left over from the Big Bang, the search for extraterrestrial intelligence, measuring magnetic fields in star-forming regions, looking for near-Earth asteroids, and modeling radio emissions from Jupiter's radiation belts. He has done radio astronomy from large telescopes, mountaintop research stations, the South Pole, high-altitude balloons, and of course, spacecraft. Additionally, he is currently the lead scientist for the Goldstone Apple Valley Radio Telescope project, in which students learn about science by doing real science. He is also an elected member of the Board of Education in Culver City, California, where he lives with his wife and 3 children. Ladies and gentlemen, please help me welcome tonight's guest, Dr. Steve Levin.
Hi, everybody. So, as you just heard, I'm going to talk to you about Juno and what we learned at Jupiter. And I'm probably going to try to rush through all the slides to make sure we have time for questions at the end, because questions are my favorite part. But if I'm going too fast, let me know. And save up all your questions and ask me a ton of questions at the end, because as I said, that's the fun part. Okay, but first, let me tell you a little bit about what Juno is, what we're trying to do. So Juno is a solar-powered spacecraft. As you just heard, it's been orbiting at Jupiter since 4th of July, 2016. And it's in a 53-day orbit, so every 53 days, we have a close flyby of Jupiter. We get a whole bunch of data for a couple hours, really. Say 8 hours total, and most of the really good stuff is within a couple hours of our closest approach. Then we spend 53 days really far from the planet, come around again, and do it again. So we get this big burst of data every 53 days. We've done a dozen or so of those so far, and what we've learned has been just absolutely amazing. Our picture of what Jupiter is like and what it's made out of and what it looks like is completely different than it was before we got there with the spacecraft. So before I tell you all that stuff, I need to talk a little bit about what we're doing. And it's going to seem like I take forever on this slide, because I do, but don't worry, I'll be faster on all the others. All right, so there's 4 main things we're trying to do at Jupiter, 4 main science goals. We're trying to understand the origin of Jupiter. How did the giant planet form? And that's really important, because if you want to understand how solar systems form, Jupiter is a really good place to start. If you want to know where the Earth came from, where do we come from, you need to understand where Jupiter came from. And the simplest way to understand that, to picture that in your mind, is to think about our solar system and how it formed. And what we know is basically 99.5% of the mass in the solar system is the sun. So almost all of it is the sun, and the sun formed first. Of that remaining 0.5% or so that's left, more than 2/3 of that is Jupiter, and Jupiter formed next. All the other planets and asteroids and comets and all of that stuff that we see in our solar system are formed after Jupiter, and they're in that little bit of, 1/3, less than 1/3 of what's left after you take out the sun and Jupiter, right? So you can think of it as Jupiter formed from the leftovers of the sun, and everything else formed from the leftovers of Jupiter. So if we want to know how did the solar system form, it's really important to understand how Jupiter formed. And a couple of the things that we didn't know before Juno got there that'll really help us are to understand how much water there is in Jupiter, and to understand the mass of Jupiter's core down inside. Jupiter's a gas giant, so it's made out of mostly hydrogen and helium, just like the sun, that sort of composition. And all the heavy stuff inside Jupiter, tells us about the origin, much of that will have sunk down into the middle and made a dense core down in the center of the planet. We needed to know how big that core was. Likewise, if you look at the solar system and say, what are the elements? What's the solar system made out of? The most abundant element is hydrogen. The next one is helium. And the third one is oxygen. So if you think about it, hydrogen is a gas, helium is a gas. The first solid you're going to get is going to be water, H2O, 2 hydrogens and an oxygen, because oxygen is the third most abundant thing. So our theories of how the planets form revolve around water. We think that Jupiter probably formed from asteroid-sized pieces of ice colliding together and sticking till you had enough so that its gravity could hold the hydrogen and helium and make a giant planet. If that's what happened, then we should find water in Jupiter, and how much water we find should tell us whether it worked that way, whether it was smaller pieces of ice, whether Jupiter formed far from the sun where it's really cold, or formed closer to the sun where it is now, where the ice, water still makes ice, but maybe the other elements don't stick to the ice the same way. So the ratio of how much water there is to how much of the other stuff there is tells us a lot about how Jupiter formed. So those are two big things we want to find, the core and the water. And then we want to understand the interior of Jupiter in general, right? What we see from the Earth is just clouds in the top of Jupiter's enormous atmosphere. It's 300 times the mass of the Earth. It's bigger volume. You could fit 1,000 Earths inside. And we see this amazing structure that you see in the picture there with belts and zones, those orange and white stripes. Those are jet streams moving at hundreds of miles an hour. We don't see beneath those from the Earth. Until Juno got there and started doing measurements, we had very little understanding of what the atmosphere of Jupiter was like underneath those clouds at the very top. And the planet, of course, is mostly atmosphere. All right, so that's a big thing we want to understand. And to understand the interior of the planet, we need to understand about the core down inside. We need to understand how deep those belts and zones go. We need to understand how everything moves interior to the planet. Then, of course, it is giant planet. We want to understand its atmosphere. It has the great red spot. It has a storm bigger than the entire Earth. It has the jet streams that I mentioned. It has all these motions and all these deep storms that we can learn about to understand Jupiter, and also to understand about how weather works in general, and maybe even understand about weather on other planets by having Jupiter to compare with. And finally, because of the orbit we're in, our spacecraft, remember I said it starts out really far away from the planet, and it comes in and it orbits over the pole. So if you watch in that little movie, you see the little imaginary spacecraft flying by. What that means is that when it goes over the pole of Jupiter, it's crossing all the magnetic field lines. If you think of Jupiter's magnetic field like the Earth's magnetic field, shown as those white lines there, looking curly here, these things. Does it show up? Yeah, you can barely see the arrow if you're looking. So if you look at those, right, as our spacecraft comes in, it crosses all of those magnetic field lines. And that's important because out away from the planet, there's these giant radiation belts, high energy particles that can fry the electronics on a spacecraft, that generate radio waves, that produce aurora lights in the northern and southern lights in Jupiter's atmosphere when the particles hit the atmosphere. All of those particles are arranged by the magnetic field. In general, charged particles spiral around the magnetic field lines and follow them up and down. So if you measure the particles in one place on a magnetic field line, you're learning a lot about what they do everywhere on that same magnetic field line. And because we're coming over the pole, and because the planet's rotating, we cross all the magnetic field lines. So we can measure the particles that hit the spacecraft and learn about almost Jupiter's entire magnetosphere. As well, by coming over the pole, we get the first good look at the north and south poles of Jupiter, and that includes the aurora, the lights, as I said, that are generated by particles hitting the upper atmosphere. So we learn about the magnetosphere that way. We learn about the radiation belts by taking pictures of the aurora at the same time as we measure the particles that are hitting the spacecraft that will eventually go down and hit the planet and make the aurora. Okay, so we have a great vantage point to see the magnetosphere. We have a bunch of instruments on board to do that, and I've color-coded them with yellow to match that yellow text. And then, as I said, we're trying to understand the atmosphere. We get at the atmosphere in a number of ways, but one of the key ways that we study the atmosphere of Jupiter is with the microwave radiometer. So what it's doing is it's using radio waves because radio can see through the clouds. So we get really close to the planet, we look through the clouds with the radio waves, and for the first time, we can see beneath the clouds and look at Jupiter's atmosphere in the radio. So that's one way of seeing into the planet a little bit and learn about the atmosphere. It's also how we try to measure the water, because water absorbs microwaves. So the more water there is in the atmosphere, the less we can see inside. The less water there is, the deeper we can see. So by having a bunch of channels on the radio receiver that see different depths and measuring how deep they really see, we can learn about how much water there is in Jupiter's atmosphere. And remember, water was one of the numbers we really care about. Then to understand that interior, we want to know about this core. There's a dense core way down inside the planet. So you might think, well, our goal would be to drop something in and go all the way down to the core. But the problem is that Jupiter is so huge, it's so much mass, that by the time you get a tiny fraction of the way into the planet, the pressure from all that mass above you, the gravity is squeezing it so much, the pressure gets up to 10, 20, 100 times the pressure here on the Earth. By the time you get a quarter or a third of the way in, the pressure is millions of times the pressure here on the Earth. We don't know how to build anything that can survive that and get down at the interior. So we have to measure that core without touching it. And the way we do that is we use gravity, because gravity comes from the entire planet, including the core. And we use the magnetic field, because the magnetic field comes from deep inside the planet. It comes from an ocean of liquid metallic hydrogen inside Jupiter. So of course, you know, I talk about Juno a lot, and I get to say that phrase, liquid metallic hydrogen, a lot. And every time I do, I always want to stop and make you think about all three words. It's liquid metallic hydrogen. So if I had a balloon full of hydrogen here in the room, it would float up into the sky. It's the lightest element there is. But on Jupiter, a quarter or a third of the way or so into the planet, the pressure gets up to about 2 million bars, 2 million times the pressure here in the room. That pressure is so high that not only is hydrogen gas squeezed down so much it becomes a liquid, but in effect, the electrons are squeezed right off the atoms. It conducts electricity. It's a liquid metal. It's the swirling motion of that liquid metal hydrogen that makes the magnetic field. So by measuring the magnetic field, we're learning about the deep interior. And as I said, gravity comes from the entire planet. Jupiter's rotating every 10 hours, 300 times the mass of the Earth, rotating more than twice as fast. So it bulges out at the equator, right? So when a spacecraft falls past the planet, when it goes past that bulge, it speeds up as the gravity from the bulge part of the planet is pulling it forward. And then when it passes over it, it slows down a little because gravity is pulling it back in the other direction. So by measuring very accurately the speed of the spacecraft, we're in effect measuring the gravity of Jupiter and how it stretches when it rotates. And of course, a dense core in the center will stretch differently than not a dense core, or a larger one will stretch differently than a smaller one. So by very accurately measuring the gravity, we can learn about the interior. All right, so that's the basic idea of how the spacecraft works. You can see the color coding here for all the instruments. You can see this orange stuff, that represents the radiation belts. Jupiter is surrounded by high-energy particles trapped in its magnetic field, and they're a danger to the spacecraft. So we have to that's one of the reasons we're in this big 53-day orbit, we have to try to go quickly through the radiation belts so the electronics don't get too damaged. And we go really close to the planet, both because we want to measure things and get really close, and because there's a gap in the radiation belts near the planet. So all this stuff trapped in the high energy particles trapped in the magnetic field is dangerous to us, and we want to avoid it. Unfortunately, it goes around Jupiter like kind of a big donut, and we can fly over the top of it where there isn't too much radiation, get way far away from the planet, and then come back again every 53 days. So that's what we do, and I'm finally off this slide. Okay, so what you all want to know is, what have we learned, right? All right, so we've published about 80 papers or so far, and we have another 100 or so in the works. So at about a minute per paper, that's about 3 hours, which means I'm not going to tell you everything, and I better give you the short version. So here's the short version. it's a whole new Jupiter. Every major area in which we measured things for the first time, every way in which our experiments, our spacecraft, was doing something new at Jupiter and looking at it in a way that hadn't been done before, we found big surprises. All the stuff people thought they knew about Jupiter that we went to measure, the original theories were wrong. They needed to be fixed based on the data. So as somebody who measures stuff, as an experimentalist, that's really fun. Making the theorists throw out all their theories is really great. And we got to do that a lot. All right, so let's go through a few of them. As I said, I'm not going to be able to tell you everything, but I'll tell you some of the highlights, and then I'll take questions at the end, and maybe we can talk about other stuff. All right, so very first thing, pretty much, first day we got good data, which was August 27th, 2016. We went into orbit on 4th of July, 2016, but since we were firing the main engine and going into orbit, we didn't have all the science instruments on. Came around 53 days later, and that's when we took our first good set of science data. The very first thing we saw, really, was pictures of the north and south pole of Jupiter. And they don't look anything like Jupiter does from the side. So on the right there is a nice picture of Jupiter with about how you'd see it from the Earth with a really good telescope. I think that actually might be from Cassini or something, but it's how Jupiter looks from the side. Belts and zones, orange and white stripes, the great red spot, all of that stuff. On the left is a picture of the South Pole and a picture of the North Pole from our first pass. So of course, it's only half lit by the sun, right? You have to go by again and get Jupiter in a different rotation to see the rest of it. But already you can see from that it looks like you're looking at a different planet. It doesn't even look similar. So all these things that you're seeing that look kind of like craters or something, those are storms. Those are storms, most of them, or many of them, bigger than the whole United States. Bigger than continents here. And there's storms in the north and in the south, and they last for a really long time. There's a zillion of them. And we don't see the continuation of the belts and zones. We don't see the kind of pattern we saw at Saturn. Basically, this was a big surprise. And there were more surprises to come just from that, from looking at the north and south poles. So what you're looking at now is a composite image where we've put together a bunch of different views so that we can get the whole, in this case, I think that's the South Pole. And we've exaggerated the color. So the color's been stretched. It's not that blue at the South Pole, but it's definitely bluer at the South Pole than it is at the equator at Jupiter. And no, we don't know why yet. But for some reason, the gases we're looking at Jupiter, it's got to be something about what gases we're seeing, so it's different composition, is bluer up near the poles than it is down at the equator. And there's circumpolar cyclones. Now those are a little hard to see in this visible light picture because we had to make a composite image and it's lit from the side and you're learning a lot. We get to watch them and see some details, but we see different details with the infrared camera. So here's the Italian-made infrared camera, GIRM it's called, because Jovian Infrared Auroral Mapper, because its main job is to look at the aurora, the northern and southern lights on Jupiter, but does a great job of looking at the poles. And what you can see is 5 cyclones gathered around the South Pole in a pentagon with another cyclone in the center, and 8 cyclones gathered around the North Pole with another cyclone in the center. And that pattern is pretty stable. We've been watching it for almost 2 years now, and it hasn't changed. They're slowly drifting around a little bit, but it's basically this stable pattern of 5 in the south, 8 in the north. We don't know why it's 5. We don't know why it's 8. People are working on a lot of theories about why the cyclones should be there, and are starting to come up with some models that maybe can explain it, but this was a big surprise. And then if you look carefully at this, there's another really interesting feature of this. These are all cyclones. They're not anticyclones. They're all spinning the same direction. So if you imagine this cyclone spinning around and the one next to it spinning around, and picture what happens in between, and if this one in the center is spinning the same direction, what happens in between? It's not like gears that can spin and match up. To do that, you'd have to have some of them spinning in the opposite direction. So in the place right in between the cyclones, you've got wind going really fast in this direction, and right next to it, wind going really fast in the opposite direction. So something has to be driving that so they don't all stop or swallow each other or do something to change that situation. So this is a really interesting puzzle for the atmospheric folks to work on. That was probably our first big surprise at Jupiter, was seeing all these storms and seeing how different the poles look. But the infrared camera, you can also learn about not just, you can see in the dark so you get a cleaner picture, but you're seeing the temperature in the infrared. You're seeing the glow from the fact that these gases are warm, and warmer gases glow more. So by measuring how bright it is, you're measuring what its temperature is. And Jupiter is warmer on the inside than it is on the outside. And the reason is that it's still cooling off 4.5 billion years after it formed. It's so big that its heat of formation hasn't escaped yet. But the result of that is, if you know the temperature, you know something about the depth. So we were able to make this little movie, which I think is about to start, and show in 3D something like what those cyclones look like. Things are thousands of kilometers across. All right, so we could talk about just the poles of Jupiter for an hour, but let's move on and get a couple of other things fit in here. So remember I said we're mapping Jupiter's magnetic field. Well, because we're in a polar orbit, we can, and in a big long one at 53 days, we can take advantage of that orbit and adjust the timing of when we go by Jupiter each time to get a different stripe. So what you're seeing is lines to represent the path of the spacecraft in the rotating field, point of view of Jupiter. So if you were somehow magically standing on top of the clouds on Jupiter and spinning around with it, that's the path you would see the spacecraft take for each of our many orbits. Which means when we're done with all of the orbits, with 32 orbits around Jupiter, we've cast a net over the planet. And if we measure the magnetic field along the way on all of those orbits, then we've surrounded Jupiter and measured the magnetic field completely surrounding it. So if you know a little bit about electromagnetics, then what that tells you is if I've measured the magnetic field on a surface, then I've learned what's happening with the currents inside that surface. Or to put it another way, if I measure the magnetic field all around Jupiter, then I know what that liquid metallic hydrogen is doing deep inside. We can understand the dynamo that generates the magnetic field by measuring the magnetic field on a complete surface that encloses the planet. So that's the goal of the mapping experiment. Now, of course, we've only completed a dozen or so orbits so far. And as you saw in that map, we do them in an order so that the first 4 are evenly spaced, and then the next 4 fill in so that we get 8 evenly spaced around the planet. And then it takes a while. You need 8 more to get 16 filled in around the planet. So we've got 8 evenly spaced orbits around the planet so far, and a few others that'll go into the next map. But the magnetometer team made a map of the magnetic field on Jupiter based on those, on the 8 good ones so far, right, that were evenly spaced. And that was a big surprise. So what's being shown here, we're just superimposing on Jupiter a map of that magnetic field where it shows you the strength of the magnetic field, and of course magnetic fields have direction, the direction of the magnetic field. So red and blue show you into the planet and out of the planet. And what you can see is, doesn't look like a dipole field like the Earth's, a nice smooth thing coming out of the North Pole and going into the South Pole. It's got all kinds of variation and all kinds of spatial variation, much on a finer scale than we expected. So more variable on smaller patches on the planet, right? And it's also got a whole lot more variation in the north part of the planet than in the south. I'm going to run that little movie again, just because it goes by kind of fast. So you can see it again and watch for this time as you see all this map, how this map shows up. We have all these wiggles up in the northern hemisphere, and a blue spot showing up near the equator. So a local place where the magnetic field is stronger and somehow coming out of the planet, and kind of smooth in the south. So it's asymmetric. It's got a lot more variation in it. If you think about what that means, what it tells us about the liquid metallic hydrogen deep inside, is it says that at least part of it, the part with all those wiggles, part of the magnetic field, must have been generated closer to the surface. Because if it was generated way down inside, then what we would measure from our spacecraft that stays up above the planet would have smoothed out by the time it got to us. All of those wiggles are telling us that the magnetic field is generated higher up in Jupiter's massive atmosphere than we expected. So instead of being all of it generated down in the liquid metallic hydrogen, it looks like maybe part of that magnetic field is generated above the liquid metallic hydrogen, maybe in a place where the gas is partially ionized, where it conducts a little bit of electricity, enough to affect the magnetic field. And then, of course, we have to try and figure out why it's so asymmetric. Why does the north look completely different from the south? And people are working on it, but as you might imagine, nobody expected that, and nobody really has that wired yet for exactly what's going on. So that was the next big surprise, is the magnetic field just doesn't look like the models. Matches great out far from the planet where we had models and we measured things before, but these are the first measurements that get really close to the planet. So you do a first kind of measurement, you get surprised. All right, so let's move on to the next major measurement we do that's different than anything's been done before, is the microwave radiometer. So as our spacecraft goes by the planet, it spins, and the microwave radiometer, in 6 different channels, looks out from the side and observes Jupiter. It's not a radar, it's not transmitting anything in the radio, it's just looking at the natural radio emission from Jupiter. But we get to look at any given point along the path at a wide range of angles. As you can see, as the spacecraft moves along, each time it spins, it's in a different place, and it gets to look at Jupiter from a different angle. So that means I have these 6 different channels that see 6 different depths, and I also get to look at them with each channel at every spot at a wide range of angles. So it's kind of like doing a CAT scan. I can kind of dissect what's going on inside Jupiter. And the radiometer just measures the brightness. It's not making a picture, but the spot that it sees, because we get so close to Jupiter, gets pretty small. So this is an example to show you how small the spots get. When we're really close to our closest approach, when we're right in there near the equator, we can see this tiny little spot. We're really measuring pretty precisely what we see on Jupiter. And then, of course, as we're further away, we're seeing a bigger part of the planet. So what did we learn by looking beneath the clouds for the very first time? Well, we only see a few hundred kilometers beneath the clouds. So on the scale of Jupiter, that's tiny, right? It looks like a thin line there. But if you think about what the planet's made out of, right? It's this gas giant. It's all hydrogen and helium and other stuff that should be all swirling around gas. So what everybody thought before the spacecraft got to Jupiter was, as soon as you get deep enough to get below the clouds, so you get below where water and ammonia, because there's ammonia on the planet, where water and ammonia condense and make clouds, once you get below that, you should be below the weather layer, below all the storms, and it should just be evenly mixed. So what we thought was our deepest channels that see as far into the planet as we can, a few hundred kilometers, since they're seeing well below all those clouds, they should have found the same thing everywhere we looked, and all the structure should have been up above the clouds, or up in the area where the clouds are and higher. All right, well, you know the theme of this, so you know what I'm going to say. Didn't look anything like that. So what we did, the easiest thing to do first, so that's what I'm showing you, is to measure the opacity, how much it absorbs the microwaves. And most of that's done by ammonia. So measuring the ammonia was the simplest thing to do first. And what we found when we did that is if you take this strip where we were close to the planet, and you spread it out, and you plot up at the top of the clouds how much ammonia there is, using color to show the ammonia, and down at the bottom how much ammonia there is, and everything in between, what we see is, as deep as we can see, we're seeing structure in the ammonia. We're seeing this place north of the equator, just north of the equator, where the ammonia seems to be uniform with depth, or maybe even getting to be more ammonia up at the top than down at the bottom. And right next to it, just north of it, there's this place where there's a whole bunch of ammonia missing before it gets down to the well-mixed part. And this part, all the way at the bottom, we're showing that as the same ammonia all the way across. That's because that's the deepest we can see. We don't know how much ammonia there is all the way down at the bottom beyond that. So we said, well, if it's well mixed, how deep can we show that it's not well mixed? And it's as deep as we can look. So it could actually have structure that goes even deeper than that. And then we see, if you look carefully, you're seeing more ammonia over here, and then some missing as you go down, and then more below that. So this was a complete surprise and a big mystery as to what the heck's going on. People have been working on that for a long time now. We're starting to make inroads. We're starting to have ideas about how this can happen and what it says about the circulation deep within the planet. And of course, one of the things we need to do is measure the rest of the planet. Remember, our orbit gets really close here and is not as close to Jupiter up here over the poles. But as the orbit progresses, each orbit shifts a little bit. So that closest approach part, the perigove, starts out down near the equator, and it moves up a degree every orbit. So by orbit 30, we'll be up here and be getting data up in that part of the planet. Anyway, I'll show you the first 9 or 10 orbits. Now what I did is I took that same map and I just spread it out. So this is latitude, -40 to +40. This is depth. It's written in pressure, but think of that as up at the top of the atmosphere, and this is, say, 350 kilometers down inside. And as you go around the planet and look at the multiple stripes we've got, you see, sure enough, at some longitudes, it really is more ammonia up here than down here. But this zone of ammonia that spreads all the way up to the top is there at that latitude everywhere around the planet. So it's like a ring around the planet at a latitude of a few degrees north of the equator. Why is it at the equator almost? Why is it north and not south? Why is it not matching up with the belts and zones very well that we see at the surface? Nobody really knows. Why is there ammonia missing here? Why is there this inversion? These are all puzzles we're trying to figure out with lots of ideas, but we need a lot more data to try to figure them out. We need to spend a lot more time basically building new theories, because we made the theorists throw out all the theories they had, which was really lots of fun. Okay, you can also, by looking at that, we have lots of longitudes now, you can see some other things that are really nice to see as an experimentalist. The fact that we're getting the same answer over and over is really good, because it means our instrument's nice and stable. If there were problems with the instrument, where if we're generating more noise than we thought it was, or if we had the gain wrong or things like that, then we wouldn't get this nice self-consistent picture. And then we can also see some little details as you go to different longitudes. So if you watch over here, for example, you can see sometimes there's more or less ammonia over here. This thing moves around, that varies a little bit, and every once in a while we see something at great depth. And that thing we're seeing that comes down here at about minus 20 degrees latitude at great depth is the Great Red Spot. So one of our passes, we flew right over the Great Red Spot. And what we found was another big surprise, which is the Great Red Spot goes as deep as we can see. So about 350 kilometers at least. The models, people had theories about how the Great Red Spot worked and models of predicting what it should be and all of that. And in general, they expected it to be a lot shallower than that. So now we have to explain why is the Great Red Spot so deep and how does it work? And we have some people working on that and some papers that'll come out before too long. And I probably shouldn't spill the beans on those papers until we know that everything's right. But you can tell to look at it, if you look at this picture at the top, that's the visible light picture, so you can see where the Great Red Spot is. And then you can see from the red here that we've got the center of the Great Red Spot looking cold in the upper channels. So I get down to 10, 20, 30 kilometers or so, maybe even as deep as 50 or 80 kilometers, and the Great Red Spot is cold in the middle. But when I get down to 150 kilometers or 350 kilometers, the Great Red Spot is hot in the middle. We still see it. Still definitely looks different from all the other passes that didn't go over the Great Red Spot. Looks different from the surrounding territory. But something is changing. It's going from hot to cold as we go down. And then there's this hot region just to the side of it that's changing and merging down with the bottom. So we're definitely getting a very interesting picture of this storm. And remember, it's a storm bigger than the whole Earth. And a lot to chew on. So I get to tell you it's a surprise, but I don't get to tell you, oh, and this is what's going on and this is how it works, because we don't have that all figured out yet. Okay, so let's move on to the next big thing, which was the gravity. Remember, gravity is trying to measure the interior. And one of the first things we got out of the gravity was those belts and zones. So remember, those are the stripes, the jet streams moving up at the top of Jupiter's atmosphere, and nobody knew how deep they went. Theories ranged from all the way down to having them go way down deep inside the planet to being really shallow up at the top. So now we know they go about 3,000 kilometers into Jupiter. And that's what this little animation is showing. And beneath the 3,000 kilometers, the rest of Jupiter rotates kind of like a solid body. Remember, it's not a solid body, it's a liquid down inside there. But it rotates all together below about 3,000 kilometers. So we learned that from the gravity. So that the belts and zones go that deep is really interesting, and that the interior rotates as a solid body is really interesting. That was a surprise. And we're starting to look at that, and it's very interesting that it's about 3,000 kilometers, because that's about where it might be conducting electricity enough to make a magnetic field. So it could be that the magnetic field has something to do with holding the inside part and why the belts and zones only go that deep. Basically, it would be that they go as deep as they're going to get as they can until the magnetic field interferes with them. We don't really know that yet. It's speculation. The other thing that we've learned, remember we were looking for the core, a dense core down inside Jupiter. So what we found is, yes, there's a dense core, but instead of a compact core down in the middle where you go down and the density is the gas and liquid and everything, and then you get to the edge of the core, you get a sharp boundary, and then now we're in the dense part. What we found is something bigger than that and fuzzier than that. Like maybe it's dissolving in the liquid or something. So we found this big fuzzy core down inside Jupiter. And now we're looking to see if there's an even denser one inside that, which will take a whole lot more gravity measurements. But again, it was a big surprise. There's a reason we're calling this the new Jupiter, right? All our ideas about Jupiter of the things that we hadn't measured yet were wrong. And we have a new picture of Jupiter now. All right, so that's the exciting stuff, some of the exciting stuff from the gravity. And I see I better hurry if I want to have some time for questions. So let's talk about the magnetosphere, the aurora. So that also was lots of big surprises. First of all, they're a lot more complex than we expected. So what you're looking at here are ultraviolet images of the aurora, where we've taken lots and lots of pictures and added them up to make a composite, sort of the average northern and southern lights. How many people here have seen the aurora on Earth, have been up to see the northern lights or down south to see the southern lights? So a smattering of you anyway. Well, to give you an idea of comparison, right, to something to scale it with, this auroral circle, if I plop the Earth down on it, the whole Earth, maybe it would, fit in there somewhere. So these are enormous. The auroral lights on Jupiter, the northern and southern lights, are these enormous displays of raw power from particles smacking into the atmosphere. And there's an auroral oval, at least they call it an oval. You can see it's a little odd shape here in the north, and the south is more like a nice clean oval. There's an auroral oval that we can see from Earth, and we've seen that glow and learned about the aurora from Earth. But there we only see it from the side. So we're only seeing it as it comes around in our point of view, and we didn't get a really good look. Now we have great pictures with the ultraviolet spectrometer and the infrared camera, and great measurements with the particle experiments that measure the particles that hit the spacecraft. And we see that the aurora are really complex, and there's all this structure going on both here and in the center. And if you look at it in the infrared, you get to see an amazing amount of structure. So you see this main auroral oval, which is where most of the power is, but there's all kinds of stuff in the polar cap that we didn't really realize was there. There's this tail around it. It's easier to see in the next picture. There we go, in that one, right? So the moons of Jupiter leave a mark in the aurora. So that one is Io, leaves the biggest tail. It's this long tail caused by Jupiter's moon Io, and we get to see amazing amount of structure and things going on in there as well. So we're learning a lot about the aurora of Jupiter, and some of the things we're learning are that it's much more complicated than we expected, that we see, for example, the mechanism that makes the brightest, strongest aurora on the Earth. We see that acceleration mechanism, the way the particles get sped up in Jupiter's magnetosphere. We see that on Jupiter, and it makes some of the strong aurora, but not the really strongest part. The really strongest part of the aurora that we see is some other mechanism that we haven't figured out yet for how those particles get accelerated. We're looking for acceleration regions to see where particles are streaming down, or maybe some of them are coming up from Jupiter's atmosphere. There's a lot to learn. We've got all kinds of surprises, which, since I need to get some time for questions, I'm not going to try to go through right now. I'm going to move on to one more thing that we learned, which is a new radiation belt around Jupiter, another surprise. So the high energy particle experiment, the JEDI instrument, it's called Jovian, I forget what the acronym stands for, energetic detector of ions or something like that, that detects high energy ions found right close to the planet. There's a ring around the planet. So I'm showing you a cross section, but imagine it coming around in front and behind the planet as well. Very close to Jupiter, of ions that we didn't expect. We're seeing sulfur and oxygen and hydrogen ions. And we think that they probably started out as atoms that were ionized, had their electrons stripped off when they hit Jupiter's atmosphere and created this belt of ions trapped really close to the planet that we're flying through. So that was another discovery. All right, getting there. So another discovery that we made is actually more about people than about Jupiter, which is because the visible light camera on Juno, which is called JunoCam, we set it up basically as a citizen science experiment. So it's a camera without a real major science team to try to interpret all the data and all of that stuff. We basically took the raw data from that camera, put it out on the web, and said, hey, everybody, go play. So when we were planning which images to take, we collected input from the public about which images to take on Jupiter. When we were trying to get context of what does Jupiter look like now, because it's a gas giant, it's constantly changing. We collected images from amateur astronomers to use as context. We let the public vote on things. Then we put all the raw data out on the web and let anybody who wanted to play with that data and try to construct pictures out of it. When you take the data from a camera out in space, it's not just like snap an image and there it is. You have to put all the pieces together and collect, a red, green, and blue image together into a color image. And you have to work on matching up when you take a picture here and a picture here, put them together to make a mosaic, take into account that the planet is curved. All of that stuff that is normally done by a team of professional scientists has been done by volunteers. And they've done an amazing job. It's absolutely spectacular. What we learned is if you let people play, they'll do amazing things. So there are some, I hesitate to call them amateurs, there are some citizen scientists out there who don't get paid to do this science, but some of them in their day jobs get paid to do other kinds of image processing, and some of them are mathematicians, and some of them are artists, and they've made amazing images using the data from JunoCam at Jupiter. So this is just a snapshot. I went, a week ago or so to the website where all of this stuff gets posted and snapped an image to show you. And you can see, if you look through here, some of these are useful for getting at the science and looking at all those cyclones and storms and studying things. And some of them are artistic images where people have done, I think this one is, somebody's taken a picture of Jupiter and made it look like a painting. So we found a lot of artists got involved, and we found a lot of people, a lot of amateur astronomers who know a lot about Jupiter got involved, and there's been all kinds of things coming out of this, including a lot of science. So the message there is, if you crowdsource the science to a bunch of citizen scientists, they'll do amazing, great work. Okay, and we also have student scientists. So one of my other hats is the lead scientist for the Goldstone Apple Valley Radio Telescope project. I wasn't going to let this opportunity go by without telling you a little bit about that. So that's a project where students all over the country, over the internet, run a large radio telescope that belongs to NASA. It's 34 meters across, so a third of a football field. And they do real astronomy with it. So they're learning about science by doing real science. One of the things they do is measure the radio waves from Jupiter. Remember, Jupiter's surrounded by these radiation belts that give off radio waves. So we have an experiment, as I talked about, that looks at the radio waves from the planet. If you're trying to look at it from Earth, you have this bright radio light shining in your eyes. It's hard to see the planet in between. If you're where Juno goes, then this bright light is looking over your shoulder. Mostly you get to see the planet, but a little bit leaks in, so you have to subtract the radio light from the radiation belts. Well, the students are measuring that from the Earth with the radio telescope, and that contributes to our model of the radio at Jupiter, so they're actually contributing to the project. So we have real students doing real science, and part of the real science they're doing is working with Juno to supply science data that we need, and that means the Juno science team, of course, participates in the classroom and so forth, and in the teacher trainings, and we actually have a few teacher trainings coming up. If you know anybody, if you know any teachers who'd like to get involved with doing real astronomy, real radio astronomy, working with the Juno team and other professional astronomers, there's those 3 trainings. They can find all about it at the website for Gabbard, galileo.gabbard.org. There's online training and so forth as well. Okay, so I finally got to the part where we get to ask questions, which is my favorite part. And I put a bunch of websites up there in case you have questions you'd rather look up, or if you want to see some of the 80-something papers that I mentioned that have already been published that I didn't get to talk about. But why don't we open it up for any questions that you do have to ask me? Yeah.
Is there there a similar spacecraft that's been sent to Saturn that will do the same kind of science, or is there one planned to do that?
So I'm going to repeat the question because people who are watching it online or see the video later won't be able to tell what you asked. And I'm also going to mention, which I was supposed to do first, if you have a question, there's a microphone over there. You guys can wait online to ask the question on the microphone, and then I won't have to repeat it. But his question was whether there's a similar spacecraft at Saturn doing similar kinds of measurements. So the Cassini spacecraft spent a long time at Saturn measuring all kinds of things, doing amazing science. And its original mission was not a lot like Juno's. It was in the equatorial plane, so it went around the planet sideways instead of over the top. And it was looking at the whole system, and it was looking at the moon Titan, and it had a probe that went in and did all kinds of great science, but it wasn't the same kind of science as what we were doing. But when that mission finished, and they still had a working spacecraft and they still had fuel left, they started working on extended missions to do other things. And in the very last stage of that project, at the instigation of some of the Juno scientists who were also on the Saturn science team, they said, now that we're down to the end, go ahead and take a risk, why don't we, and let's try and fly in a Juno-like orbit past Saturn. So they did. They couldn't do all the same science that we're doing at Jupiter because they didn't bring instruments for that purpose, right? Remember, the instruments they brought were for a completely different mission, but they were able to do some of it, and they learned some things about the interior of Saturn, which I'm sure they're not ready to publish yet because it's not been very long since they did that. But we'll get to do a little bit of comparison. And we'll see, maybe someday in the future, a Juno-like mission will be sent to Saturn to really do the job the way we did at Jupiter, or to Uranus or Neptune. All right, who else has a question? Great. Yeah, go ahead.
I have two questions. The first is if you could say something about this metallic liquid hydrogen. Is it, what kind of viscosity do you have? Is it like lava or something? And the second question is, my understanding is what little we know about the interior of Saturn is there might be a level at which there's like precipitation of helium or something. Is there any kind of interesting precipitation going on inside of Jupiter?
Right, okay, so let's start with the liquid metallic hydrogen part. And I'm going to get to give you my favorite answer, which is nobody knows. But I can say a little bit more about that. So the way we know that that hydrogen, when you squeeze it enough, should make liquid metallic hydrogen is from theories that are based mainly on experiments where you take a small pellet of hydrogen, you zap it with enormous, really powerful lasers, and for a tiny fraction of a second before it explodes, it implodes and reaches this really high pressure. You try to measure what's going on in that very tiny fraction of a second. So it's really hard to do those measurements. From those measurements and from those models of what hydrogen should look like under great pressure, they made predictions that it should become a metal at about 2 megabar, 2 million times the pressure here. The biggest piece of information to validate that prediction and make everybody say, yeah, liquid metallic hydrogen is real, is Jupiter has a magnetic field. And we knew that for a long time. We've known Jupiter had a magnetic field for a long time, because even before we ever got there, because you can see the radio waves from the radiation belts that are trapped by the magnetic field. To make a magnetic field on a planetary scale, you need a liquid that conducts electricity. Jupiter's mostly hydrogen and helium, so you weren't going to have molten iron like on the Earth and generate anything near as big a magnetic field as what we see on Jupiter. So just the fact that it had a magnetic field confirmed the hypothesis that yes, hydrogen makes liquid metallic hydrogen. But we don't have good measurements of the viscosity of liquid metallic hydrogen. What we have is theories about what it ought to be like. And the conditions under which it's moving are really high pressures. You know, at 10 million times the pressure here on the Earth, it's hard to even talk about things as a liquid or a gas or a solid. It's different. So that's kind of the state of knowledge. And we'll learn by measuring the magnetic field. Remember, we're going to keep mapping and get more detailed map of the magnetic field. When we finally understand the dynamo well, that will also be teaching us about the properties of hydrogen, what hydrogen does under great pressure. So we start out with, how does hydrogen behave? Let's use that to figure out the dynamo. eventually we may figure out the dynamo and use that to tell us how hydrogen behaves. Okay, and I'm forgotten, what was your second?
The precipitation stuff.
So yes, so there's probably helium rain going on at Jupiter. Exactly how much and where is something we're still working on, but should come out of our data. There's water rain, no doubt, on Jupiter. We see that in, we've seen lightning at Jupiter before. We know that there's liquid and solid water and water in the gas state. How deep that rain goes, possibly has something to do with that bizarre structure we saw in the ammonia and how the atmosphere works at a few hundred kilometers below the surface, but we don't know those answers yet.
I was in graduate school in the early 70s, and they were talking about speculations of metallic hydrogen in Jupiter then, without any ability to measure anything. Thank you.
Thank you.
Are we beginning to understand the really startling differences between Jupiter and Saturn?
Well, we're beginning to understand the really startling differences between Jupiter and Saturn, but we've got a ways to go still. Just all the surface stuff that you see where, Saturn has these geometric shapes at the poles that have something to do with how the jet streams work. And Jupiter has this completely different chaotic looking structure out of cyclones. Tells you that the atmospheres behave very differently. And maybe that shouldn't be so surprising. Jupiter's a lot bigger than Saturn. And the heat flow in and out of it is different. But it'll be a while, I think, before anybody feels confident saying, okay, now I understand Jupiter and Saturn.
Hi, two questions. First one is, I've read that Juno is the fastest man-made object that we've ever sent out into the cosmos, but I've also read that it's not quite that simple because I guess it's all relative. So can you talk a little bit about that to the extent that you can in a way that I might understand to answer that question? Is this or is this not the fastest? The second question is, why did you include a giant can opener on one of the panels?
Okay. It's not a giant can opener, but it certainly does look like one, or a bottle opener anyway. But let's start with the speed record for fastest man-made object. If I tell you I throw a baseball and say, how fast did I throw it? Well, you can measure how fast it went, here on the ground. If I'm sitting on a moving train that's going 100 miles an hour and I throw the baseball, suppose I've got a really good arm and I can throw it at 90 miles an hour. The train's moving at 100. Maybe I threw it at 190 now because the train's 100 miles an hour plus the 90. Or if the train's going the other direction, maybe the baseball's only going 10 miles an hour. I have to define a reference frame. I have to say, how fast is it moving relative to what? Okay. So if I choose the reference frame carefully, then I get to say that Juno's the fastest thing ever built by people. And I'm not sure I'm going to remember this exactly right, but I think the way it goes is if you take Cape Canaveral, Florida, and you follow it, and you say, where we launched from moving in space as the Earth goes around the sun and the Earth rotates and Juno moves out or past the sun and so forth, then at the time when Juno hit its closest approach to Jupiter in its very first time, when we fired the main engine to slow down so that we would go into orbit, before we did that, before we fired the engine, when it was moving its fastest, I think, if I remember right, that's the reference frame in which you get to say it's faster than anything anybody else has ever sent. So it's a pretty, it's kind of a cheat. But it does tell you it's moving really fast. And that's mostly because of Jupiter's enormous gravity. So another way to look at it would be, how fast is it moving relative to Jupiter, right? So you ignore the Earth and the sun and all of the motions we did to get there, and you just say, what's the speed of the spacecraft when it goes flying by Jupiter compared to the cloud tops that it's flying by? And at its fastest, I think that number was in the neighborhood of 30 kilometers a second. So you've gone all the way across the LA basin. It's pretty fast. Okay, so the giant can opener. That's actually the magnetometer boom. So we have 2 magnetometers on the spacecraft, built by the same team, doing the same job, but it's not just redundancy. Part of it is if one of them breaks, you have another one. But part of it is one of them is closer to the spacecraft than the other. And both of them are more or less as far from the spacecraft as we could get them. So everybody, somebody here I'm sure will think of this immediately. Why do I want my magnetometer really far from the spacecraft? Right, I heard at least one person say it. I want to measure the magnetic field of Jupiter, not the magnetic field of the Juno spacecraft. So I want the magnetometer as far from the spacecraft as I can get, and I want the spacecraft as magnetically clean as we can get. And it's really magnetically clean. The magnetometer team, the guys at Goddard who built this magnetometer, worked really well with the spacecraft team to help them measure the magnetic field of parts as they were coming onto the spacecraft and to figure out ways to make the spacecraft really magnetically clean so that every time you have an electric current this way, right next to it, you have another electric current the same size going the opposite direction to cancel out its magnetic field, not using any magnetic parts, all of that stuff. So the spacecraft has a really low magnetic field and the magnetometer is really far away from it. And that tells you why we really want 2, one closer to the spacecraft than the other, because now, as the spacecraft spins around and we measure Jupiter's magnetic field, if there's a difference between the 2 magnetometers, we can tell that there's a magnetic field from the spacecraft as opposed to from Jupiter. So we can cancel that out or subtract it out and get the magnetic field of Jupiter. But it came out really magnetically clean, so it worked well. Yeah.
Thanks for having me. I have 2 questions. The first question is about the weather and the circulation of gases in the atmosphere and the magnetic field. And I'm just wondering if you can elaborate a little bit more on that. And also, is there, you talked about how the movement of gases or fluids in the quote atmosphere of Jupiter might be generating magnetic fields, and I'm curious about the possibility of the opposite effect. And then my next question is about the metallic hydrogen that you're discussing. And the discussion always seems to be as if the metallic hydrogen is pure. And I'm just wondering if what speculation has been done about alloys in which other elements or whatever elements are mixed in with that, and what effect that has on your calculations.
All right, that's going to be a lot to talk about. So, all right, let's see what we can do. Let me take it in reverse order because I remember the last question best. So remember that Jupiter's composition, while not exactly the same as the Sun, is similar, and we know what the composition of the Sun and the whole solar system is. It formed from the same cloud of material, presumably, and that's mostly hydrogen and helium. So by the time you get down even to oxygen, it's a few percent or something, right? When you get down to something that might conduct electricity or mix in with the metallic hydrogen, it's a very low percentage of the material. So if, and there probably are, if there are contaminants in the liquid metallic hydrogen ocean, those contaminants probably don't play a big role because it's such a low percentage of the total material. Now, you do have to be cautious about that. If I said, you know, I took iron and I put a little bit of carbon trace elements in it, it shouldn't matter much. You know, I can make steel, but that's a solid with a crystalline structure that's different from a liquid. And even there, I think the percentage of carbon is probably higher than percentage of trace elements in the metallic hydrogen. So I'm not going to try to go beyond that because I don't know the answers. I'm sure somebody somewhere has done that calculation about how much we have to pay attention to the impurities, but that's the rough sort of description of it. Now, the magnetic field in the atmosphere, I want to make sure that we get the picture right. So picture this liquid metallic hydrogen under very high pressure, swirling around because there's heat coming out of the planet and the planet's rotating rapidly. So, you know, the heat wants to make things rise, right? You carry the heat out, you move material around, you spin the planet around rapidly. It doesn't move in a nice, smooth, easy pattern. You get shear, so you have stuff stirred up. That's generating a magnetic field. That's got to be the bulk of the magnetic field from Jupiter. But our measurements show that the magnetic field is more complicated than we thought it should be based on that. So one possible answer, and it's by no means sure, is that higher up, just above that metallic hydrogen layer, where the hydrogen is compressed but not enough to make liquid metallic hydrogen, that maybe that conducts electricity a little bit. And we know that if you squeeze hydrogen gas enough, you can pressure ionize it. You can have those hydrogen atoms smashing into each other so much because of the high pressure that every once in a while an electron gets stripped off, and so you have a little bit of conductivity. Some of them are ions instead of atoms. If you do something like that, conduct electricity there, and it's all moving around, that could affect the magnetic field. Now, the way a dynamo works, yes, the magnetic field is definitely interacting with the motion of the liquid. So it's not you make the liquid move around and produce a magnetic field and voila, you get a field from whatever the liquid was doing. It's you make the liquid move around, it produces a magnetic field, that affects the way the liquid is moving, makes it move in a different way, that affects the magnetic field, and you get this process that's much more complicated, but in which actually the motion of the liquid can generate a magnetic field that causes it to move in that way some more and makes a stronger magnetic field. That's how a dynamo works, we think. So it's not simple, but yeah, there's definitely an interaction between the motion of the fluid and the magnetic field that it generates. Now, on top of that, if I look at the upper atmosphere, if you remember that picture with the belts and zones, the movie, this one, is that playing? Can't tell if that's starting to play. There we go. So if you remember that, we have this speculation, and it's only speculation at this point, that the fact that those belts and zones are 3,000 kilometers deep might have something to do with getting deep enough to where the pressure makes a little bit of conductivity, and perhaps below that, where the gas conducts electricity a little better, maybe the magnetic field holds it and stops the belts and zones from going any deeper. Speculation at this point. The main thing is we can tell from the measurement about how deep they go, and we can tell from the measurement that below that, the planet rotates as a solid body, and then anybody who thinks about planets can try to figure out why it does that. And of course, we have lots of people working hard on that. Even as we speak, they're probably at home, you know, thinking about things and working on their computer models. Okay. Did that cover what you were asking?
Thank you very much.
My
I
pleasure.
obviously have other questions, but I think that's enough.
Well, you're welcome to go to the end of the line and come back and ask a question
Thank you.
after the...
Mine is very simple. I just want to know, what would you say would be a difference from the hot Jupiter, from the new Jupiter? Would those, all that information be different?
I'm sorry, say the beginning part again. The difference between...
Hot Jupiters?
Oh, hot, you mean like around other stars and our Jupiter? So...
From the information you just are discovering.
Right. So it's a trickier question than it sounds. And that's because in many ways, what we know about the planets around other stars is much more limited. But of course, we have lots of them instead of just the only one example we have here. I know a lot of people, there's a bus that they're trying to catch, is why we have a bunch of people leaving at the moment. So we don't really have that comparison yet. Our guess would be that the one planet, giant planet that we have, Jupiter, is presumably sort of typical for what planets that size look like, but we only have the one. We don't have 50 of them to look at. And if you look at the planets around other stars that we've discovered, there's all these biases about how you discover them. Makes it easier to discover big ones close to the star and so forth. I will say that until people started finding exoplanets like that, no one really expected to find giant planets that close to a star. So the model of how do solar systems form still has a lot of work to go on it to understand. We think it has something to do with planets forming farther from the star and drifting inward as they gobble up the material that makes up the early solar system. And in fact, we think perhaps that Jupiter formed further from the sun, drifted inward, gobbling up stuff on the way, and in the process disturbed the orbits of what now are Neptune and Saturn and kicked them out into the outer solar system, and maybe even stirred up the things that eventually became the Earth and Mars and all the small planets. We'll learn more about that as we finally get the water content, which is going to come as we understand the atmosphere better. That'll tell us a lot about whether Jupiter moved or whether it formed where it is now.
Oh, and then also the jade, I think that's what you were referring to for the middle part of where it was measuring. I think that's what it's called, the Jovian.
We have
Is that?
2 instruments on the spacecraft that measure the particles that are hitting the spacecraft. There's the JADE, which is Jovian Auroral Distributions Experiment or something like that. And that measures the relatively low energy charged particles. And then there's JEDI, which I won't try to remember the acronym, but oh, you're right. It was on one of my very first slide. There you go. And so JEDI is the higher energy particles. It's hard to get through all of these slides backwards. There we go. Okay, good. So JEDI is Jupiter Energetic Particle Detector of ions. It must be ions because that's the I. Anyway, so we have to measure a full range of energetic particles, and then they work together, right? Because the particles don't know whether they're energetic or not energetic in terms of distributions. It's not like they come in nice little bins. So you measure that. You measure the plasma waves that are going through, so you see magnetic and electric fields. You measure the light from when those particles hit the atmosphere, so that's the ultraviolet and the infrared cameras. You measure the radio waves given off by the particles. We can do that with the microwave radiometer. We measure the magnetic field that organizes all of it, put all that together in a big picture, and that's how we understand the magnetosphere. So it's all of those instruments working together as a team to really understand the picture.
Well, that's awesome. Thank you.
Thank you.
All right, I have a very quick question regarding the cyclones. So I know we previously went over that on the same side, the cyclones next to each other, they're moving the same direction. However, I was wondering if the cyclone groups on the North Pole are moving the same directions as those on the South Pole. And if so, what is the most popular theories that we have come up with? Or even if it's speculation, that would be good too.
All right, so let's look at the pictures and we can actually answer that question. So here's the South Pole. So I'm looking at it from the south, and you can see the spiral goes around that way, right?
Yes.
Here's the North Pole. I'm looking at it from the north, and you can see the spiral goes around the other way.
The other way, okay.
Okay? So, whether that's the same direction or opposite direction depends on, the viewpoint,
Yeah.
right? But you can see which directions they're spinning that way. And then since all of these are doing the same thing, then that's why it's a problem if they're all spinning the same direction and rubbing on each other. Somehow they have to, something has to supply energy to keep them rubbing on each other, or something has to give them, a way to spin next to each other and not destroy each other. It's also true that if you take a rotating planet and you put a cyclone on it and say, what does it do? What you would expect, actually, is the cyclone will drift up towards the North Pole, or if it's in the southern hemisphere spinning the right way to do that, drift down towards the South Pole. because if you imagine, you're on Jupiter, you're a little bit north of the equator, and you're spinning around, well, the whole planet's rotating. The part that's closer to the equator has further to go all the way around the planet than the part that's north of the equator. So if I come around in my cyclone and I'm going north, then I'm shifting speeds. If I come around the other way, then I'm shifting speeds downward, right? So if you work out all the, add up all the speeds and say, what does the air do? You wind up with a little bit more speed heading north than heading south if your cyclone's spinning the right direction to be a cyclone. So you expect the cyclones to drift up to the north. That, of course, doesn't explain everything. You have to say, well, where did the cyclones come from in the first place? And why do they last long enough to spin up to the north? And why do they last long enough when they're all butted up against each other so that we see them, for 2 years so far and not much change? But at least a little piece of that puzzle is explained by just, if I make a cyclone and I don't have anything to stop it, there's no ground for it to run into, it's going to just gradually drift northward and pile up at the North Pole.
Okay. Well, has anybody made any prediction when exactly did it started, and will it ever stop, or is it just constantly going to keep going, or nobody has ever made any sort of predictions or studies yet?
Well, it's pretty new. I mean, we've been there for less than 2 years, and this was a big surprise to everybody in the first place. But one of the things we're doing is watching these cyclones really carefully to try to see how they change. So you keep coming back and you look at those 5 cyclones around the South Pole, and they're always there every pass. But if you take a really good look at the images and compare, they're shifting a little bit. They're not just rotating in place, they're moving a little bit. So we're trying to start tracking them and use that to try to understand how long do they really last, and what do they do, and how do they move, and all of that stuff.
Do you have a specific website that's dedicated to this that I can sort of follow to see the tracking and all those data?
I don't think so. I think your best bet for that is to keep an eye on NASA's website for Juno. If you look at, nasa.gov/Juno, or on missionjuno.swri, which is the more sort of public-friendly version. They're both fairly friendly, but that's the one that's also got all the JunoChem stuff. I'm switching through to get to the websites because telling you the name is probably not going to be easy to remember,
Okay.
but you can write it down or find it online. Probably the place to do is follow there, and of course we'll publish things in the scientific literature, but that's going to be a while.
Okay.
It's a good question, though. Maybe we should think about whether there's a way to take the different scientific questions and put them out there and let people follow the story a little better. But
It would be great if everybody can take votes on like which sort of data they want to follow, and then you can open up like a tab on the website just dedicated to those data and constantly updating them every month. That would be awesome.
I like the idea, but I'm also picturing the people who would have to do that saying, we don't have anywhere near enough people to do that. All right, thank you.
All right, thank you so much.
Yeah.
Hi, I have 2 questions. The first is, do you think that the fact that there are 8 cyclones in the North Pole and 5 at the South Pole, does that have anything to do with the fact that the magnetic fields seem to be more turbulent in the north? And my second question is that it seems like most of the science is coming from the flyby period of Juno. Are we collecting any data from when it's like the rest of its orbit?
Right. Okay, so about the cyclones and the magnetic field, it's striking that the planet is asymmetric in its magnetic field and in its atmosphere as seen at the top, and in its gravity signature. But it's hard to picture how the magnetic field could be influencing those cyclones, because up at the top of the atmosphere, where at pressures similar to the pressure here in this room, the gas doesn't conduct electricity very well, so it shouldn't be affected by the magnetic field much. And it's got huge amounts of mass moving at pretty good velocities. These are cyclones, right? Think of, the power in a hurricane here on the Earth, and now you're talking about storms that are bigger than the biggest hurricane you've ever imagined. So nobody has yet come up with a mechanism that explains it, that connects the asymmetry in the magnetic field with the asymmetry in the weather. I'm not saying it's not possible, but I haven't heard an argument that works or anything where the math plays out at all. What was the other thing you asked?
If Juno collects data on the rest of its journey.
Data away from Perigove. We call that part where we get really close to Jupiter, Perigove, near Jupiter, Perigove. And the most important science data in general is from Perigove, as you said, from within a few hours of our closest approach. But yeah, we don't turn the instruments off for 53 days when they're out far from Jupiter, and there's other things we get to measure. In particular, a lot of the fields and particles instruments get to measure a lot of interesting stuff about the magnetosphere, because Jupiter's magnetic field stretches way out there, and our orbit is big enough that we cross lots of interesting regions quite far from Jupiter, and we do those measurements. It's not the prime science we went there for, but it's lots of good stuff, and we're collecting lots of data. And the microwave radiometer that does those atmospheric measurements, the data right up next to Jupiter are way more valuable than any of the rest of the data from the microwave radiometer, but it doesn't use up a lot of bandwidth to send that to the ground. We get to learn about the radiation belts a little by seeing them in the radio, and microwave radiometers don't like to be turned on and off. So we just leave it on, let it run, and collect the data, and all we do is throttle back the data rate a little bit when it's away from the planet, so we won't be wasting the communication with the ground, because you can only send so much data at a time. But we just leave it on, and I think it's about 1/7 of the data rate the whole time, just because it's safer for it to never turn it off.
Thanks.
Sure.
Hi, I had a question about the consistency of the magnetic field measurements over multiple years. Given that it's being generated by a fluid,
right,
it would seem reasonable that maybe over the course of multiple years that would shift, and so the map is actually changing and not like a consistent map.
Right. So we are looking for variation in the magnetic field over time. But you have to remember, Jupiter is so big that it's really hard for us to picture the timescales involved. So we're going to be at Jupiter if everything goes well, and imagine the spacecraft lasts for a really long time and we wind up doing an extended mission and all of that stuff. Suppose everything goes perfectly and NASA says, sure, do whatever you want, we'll give you lots of money and all of that. Maybe the spacecraft would be around for another, I don't know, I'm totally making it up, but say 10 more years, right? It's not going to be beyond that, because the radiation sooner or later is going to kill it. Jupiter's been around for 4.5 billion years. It hasn't even finished cooling off yet. The motions in the interior, suppose that dynamo is like shifting like crazy on a flash of a timescale on Jupiter's timescale. That still might be 500 years. So yes, we are looking for variation in the magnetic field. We hope that as we get through all our 32 orbits and maybe an extended mission or something and go beyond that, that we'll be able to tell whether the magnetic field is varying. But given that, of course, Jupiter has surprised us a bunch, we don't expect it to be varying on timescales of a year or two. We expect to be able to measure really small variations in the magnetic field and say, yeah, I think if you waited 1,000 years, it would do this.
Cool. Thanks.
Sure.
Perhaps this hasn't been determined yet because you got to finish the mission, and then just alluded to possible extended mission. But at some point, do you anticipate that Juno is going to meet the same fate as Cassini because you have to protect Europa in particular? Yes.
So right now we're on a plan where we do 32 orbits, 32 science orbits, so it's a few more, with a spare or two to make sure we get all the longitudes and do the magnetic map. And then at the end of that, we fire the thrusters so that it dives into Jupiter's atmosphere and burns up. That's the plan we're not even asking for an extended mission yet. That's going to be 2021 by the time that happens. But presumably, if everything works great and we're able to show NASA that we can protect Europa without destroying the spacecraft right away, then we would figure something out and we'd ask and see if they're willing to let us operate it longer. We're in the prime mission. We're not ready to work on that. And we have a requirement to make sure that we don't contaminate Europa. The simplest and most straightforward way to not contaminate Europa is to vaporize the spacecraft in Jupiter. You can come up with more complicated things, and I'm sure nobody's going to want to destroy the spacecraft without needing to. I'm sure when the time comes, if somebody comes up with a clever plan, we'll go argue, hey, look, Europa's safe enough, let us do this another, so many orbits. But right now, we're on a plan, and the plan has it in orbit. I think it's orbit 36, if I remember correctly, but something like that. So after 32 science orbits, plus a couple of spares, plus there were 1 or 2 at the beginning that weren't science orbits, we'll fire the thrusters and deorbit and burn it up in Jupiter, which is essentially what Cassini did. And as you know, Cassini did, extended missions until finally they had to, give up and say, okay, we can't do this anymore. We're going to run out of fuel, and we have to protect Enceladus. So the thrusters are just gas. We had hydrazine and an oxidizer to fire the main engine, but we're not using the main engine anymore. The thrusters that control the attitude and shape the orbit now are just blow a little gas out from the fact that the tanks are pressurized. And that's the limiting factor for fuel. Limiting factor for lifetime might very well turn out to be radiation damage. We haven't seen any significant radiation damage yet, but there's a long mission to go. But that's the kind of thing that probably limits the technical lifetime. And then, of course, we're at the discretion of Congress and NASA to decide whether they want to keep paying to make this happen. If we got to the point where we weren't getting great science or it wasn't worth the money, then that could also be a limiting factor. Yeah.
Looking at the 2 spacecraft, Voyager and Juno, Voyager was launched in 1977, Juno about 3 decades or more later. And with the limited capability, especially with the computer we had at Voyager, now Juno is much more. Voyager just flew by, and we learned a lot about Jupiter from them. Can you just briefly tell me in those 3 decades what we learned? We had also Galileo in between.
Right.
I'm sure that we learned a lot, of course, and between. The interesting thing that I see the 2 spacecraft next to each other.
Right. Well, I do want to point out that, that's a full-scale model and that's a 1/5 scale model. But the way I would think of it is big picture. We explore our solar system first with, let's just get to the planet and see what we can learn. And you learn a lot from the very first flyby. And so Voyager was about that, was about getting from one planet to the next and learning an enormous amount of stuff because no one had ever been there before and everything was brand new. Galileo was, now we've learned something about Jupiter. We know what questions to ask. We know what the spacecraft has to be able to do to survive. Let's go put something in orbit and study the Jovian system. So it studied the whole system, right? The moons of Jupiter as well as Jupiter itself. Learn about the magnetic field and the magnetosphere and all of that. And then after Galileo, it dropped a probe into Jupiter and learned a little bit about the atmosphere. And one of the key things we learned from the Galileo probe was that 20 bars, going down to a pressure of 20 times the pressure here on the Earth, wasn't enough to get to where the water was well mixed. So people thought they were going to measure the water content, the global water content of Jupiter with the Galileo probe. And then what we found is we measured the water. The probe did everything it was supposed to do, but Jupiter was more complicated than that. And it found big surprises. It found the composition of Jupiter had these heavier elements besides hydrogen and helium at like 3 or 4 times what they were expected to be. So it sort of matched the proportions in the sun. If you took an element, divide how much of carbon there was, divide by how much hydrogen there was, compare that with the ratio in the sun, everything was off by a factor of 3 or 4. There was more of the heavier stuff, except for water, where it found hardly any water. So that was a big mystery. It was one of the key reasons we sent Juno there, was to respond to that mystery and try to measure the water, try to see the greater complications, and do a more specific measurement. So Juno doesn't try to study the whole Jovian system. It doesn't try to study multiple planets. It tries to study Jupiter and specific aspects of Jupiter that we now know to ask questions about and get into much greater detail. So you go from a flyby that's going to try to study multiple planets and learn the big broad brush stuff that nobody knew yet and do raw exploration, to an orbiter that's going to stay in the equatorial plane and study the whole system, so not multiple planets, just Jupiter, but learn all kinds of wide variety of different things about Jupiter, to a spacecraft like Juno that's focused on particular questions and study particular things about Jupiter that had never been studied before. And I hope there will be eventually a next mission that will go and study perhaps Europa, which is a very interesting moon of Jupiter and has a liquid water ocean and is a place we could look for life, or any other aspect of the Jovian system where we have more specific, more detailed questions. So I see those 3 spacecraft as a progression in the level of detail we look at and the kinds of question we answer. And that happens at all the other planets in the solar system as well. We just recently, on planetary timescales, had the New Horizons mission fly by Pluto and do that first exploration of Pluto. I hope sometime, maybe in my lifetime or the lifetime of some of the people here, we'll have an orbiter get to Pluto and do the more detailed study using the information that they learned in that flyby. So it's that same progression. All right, I guess we're...
Last 2 from the web and then wrap it.
A couple of questions from the web. So, somebody sent in, why does the great red spot get colder below the surface? And how does adiabatic cooling work if warm at the top and cool in the middle? And I get to say my favorite answer, which is not only I don't know, but nobody knows. But there's speculation, and if you look at scientific conferences and at some of the papers that are coming out, people are starting to come up with ideas for that. So, watch this space and think about what happens if you mix up the atmosphere and look at the winds and so forth, and you can come up with models for the dynamics that might explain that. I'm not going to try to do that here tonight, both because I'm not the right guy. There's some atmospheric scientists, some really smart people working on the project, working on exactly that problem, and if I try to explain what they're doing, I'm likely to get it wrong, and because they're not quite ready to publish it yet, so they probably wouldn't like it if I said, well, they're speculating this and that and the other, and then tomorrow they find a one where there's supposed to be a 0 and they have a different answer. So I'll wait till the people working on it announce that they think they understand it. Then somebody else sent in, are the aurora on the South Pole weaker because they're so spread out? I don't know the answer to that. That's not nobody knows. That's just I don't actually remember whether the southern aurora are weaker or not than the northern aurora. So I can maybe send me an email or send it to JPL, to our outreach folks, and I will try to get you an answer to that, whoever was watching this from online. I think we probably know the answer to whether the northern and southern auroras are different strength. I just personally don't know the answer off the top of my head. All right, I guess we're out of time, huh? Thanks, everybody.